All right, let's go ahead and get started. Welcome to our very first demo day. As I was saying before I started recording, it's my favorite day of the semester. I don't have to do as much, and your teams all have to come up here and talk about your designs. I'll just sit and just listen, and I'm very excited about that. We will just go in order from team to team, and you don't have to sprint through it. I said 12 minutes max. If you take 13, it's fine. If you take 11, it's fine. If you wanted to talk for a half hour, I may have to stop you short there. If we have questions, it'd be great to have them. The designs look kind of samey for this MP-0, so when you get to be the third or fourth team presenting, I understand if you feel like you're repeating previous teams. That'll be much less the case for future assignments. But for this one, it's pretty tightly structured, and so I understand that if a lot of the designs look pretty similar, and we should have a little fun with it. Maybe we'll develop that kind of atmosphere in class over time here this semester. I mentioned the next assignment, and I think one of the small challenges with the timing and the scheduling of this course is, although it's true of all courses, but you finish this MP-0, finished it, submitted it last night. We have this presentation today, and MP-1 starts tomorrow in lab. But for all of these MP assignments, after this very initial one, we do have a pre-lab component to them. Usually the pre-lab says read through the whole lab document so that you're not spending the first hour in lab on Wednesday just kind of reading through the PDF. The MP1 PDF is probably the longest in terms of amount of words because I'm just trying to describe a lot of things with the MP1 setup, which is a little different than what we had for MP0. For MP2, MP3, MP4, it's much less setup. It's just more concepts being introduced at that point. So for your pre-lab, it's going to be a submission by team. I would want you to go into Canvas, and you can start with like a draft of what your report document may look like, or it can just be a separate file, that's fine. And you're actually going to submit that before lab starts on Wednesday. And that'll be your first submission. Once you have your final submission, you'll just then go and resubmit in Canvas for that so that Jeremy can just keep track of, okay, every team did their pre-lab. Now we separately grade that every team did their final submission as well. Here's the description for it. It's one of the first things there. Read through the document. You can skim, I think, probably on your first pass through, and then answer the questions at the end under the pre-lab questions section header. I think it's a pretty important step, and it's not meant to be busy work. It's not meant to just give you something else to do before you get started in the lab. You have those 2 Wednesdays in the lab to work on this as a team, and certainly for this one, much more so than for MP0, it'll be a struggle to make any good progress tomorrow if you haven't read through the assignment as a team, and if at least one of you hasn't gone through the mathematical steps required for the pre-lab here. Has anyone taken a look at it yet? Good. Okay, skim is all I was looking for now. I knew I could count on you. But everyone else will do so today. I wouldn't want you to start it at 9 a.m. tomorrow. You won't get it done in that amount of time unless you're really fast with this kind of thing. So that's intentional. So the instruction is for the pre-lab is the very first thing, but it says read through the whole document. The actual pre-lab question on this one, I probably should have put it on a different page, but I didn't. It starts here on that page 14 of review the entire document. Focus on section 5. What I'm asking you to do, pencil and paper, literally in this sense, is to just walk through at a very high level a couple of the steps we've been talking about of the graphics rendering pipeline. You're going to be writing an input vertex. We haven't talked entirely what that means, but it's going to be this XY location. Negative 0.25, negative 0.25, and it's going to have a color value. We talked a little bit about that. We'll be talking more about that soon. And just kind of walk it through. For the architecture you'll be putting in place for MP1, what should a reasonable output be of that test input values? Do it for 1 input value, you do it for 2 input values, you do it for 3 input values, and that's the entire pre-lab that we have for this one. So reading through, skimming, collectively do as a team, discuss as a team over Discord or in person, it doesn't matter, between now and tomorrow, and have that submitted before lab. I think it would be helpful for us to kind of correct any misconceptions you may have starting Wednesday versus letting it kind of simmer for a week before you get started with that. So any questions about pre-lab or MP1 or tomorrow? Okay. Today's supposed to be a celebration, not sadness. So it can be both. That's fine. So for MP0, the demo day, we'll just go team by team. Come on up as a team. Some of you are, it sounds like you're very well organized. Who's going to be talking and saying what? The rest of you are not. That's fine. Just do your best with it. If I have questions as you go, I'll ask them. Otherwise, afterwards, we'll have a couple minutes for questions. Team 1, you won't always have to go first, but you can go first now.
We're group 1. My name is Gautam. I'm Ben. Andrew. I guess we need someone to control the computer.
Yeah.
So for
Actually, can you? I'll interrupt you because you're first. Go back to slide 1. You sent the previous slide. So what were the different roles we had?
so I designed the state machine to control like our hardware accelerator, and then I integrated everything together and got to work. So I initially attempted to do the multiplication part of it, and I was really interested in VHDL, so I didn't do it correctly, the multiplier and the accumulator part of it. And then I also worked on trying to unroll things a little bit more, but we were having not as much success, me and Andrew. So that's kind of what I did this first part of the lab. So
I worked on some of the like high-level architecture, finding which kind of components we wanted to put together in orders, and then I also worked on the multiplier accumulator like computation that we had.
I pretty much just read over the code and tried to understand everything that was going on.
So by the way, a couple of those roles are pretty important, I think, right? There's 4 of you. Some of these teams will be 3. We could do the lab with 2. 4 is kind of a compromise to kind of get the teams to work numbers-wise. There's an additional student today, so we'll actually get another team of 4 starting tomorrow. But I think moral support is always important. You know, be the person who helps the team like keep going and not give up and keep it on pace. Code review is critical for this. I mean, having someone over your shoulder that you can just talk to about what you're trying to do. My only suggestion would be that, you switch off roles every so often, so you're both code reviewer for this, and then you design this component. I think that's a very nice way to break it down. So that seems like a reasonable set of roles that you have there. Although the first class, when you say FSM design and hardware integration, that's the entire assignment, right? It's FSM design and hardware integration. But I can see different parts where you would have been helpful as a team to kind of to work with each other and get things done.
So I guess one of the first parts of this was to be able to take some of the matrix data and put it through the Mac, right? And so what we did is we used the VRAM cells to load in that data into the registers, and then so each VRAM port can send 2 16-bit values across the accelerator, and which means like 4 matrix values in total. And then so we had two points of entry using like the addresses. So we had address A and an address B, which were offset by 1 each. So you could keep on, adding more, and we would add the address. We would add 1 to the address, and we can go to the next address each time and load more and more values in.
You have to add 2 then, right? Or is it still just adding 1 to the address?
Yeah, it should be 2. That's
yeah.
a mistake. Yeah.
Yeah, and then for the actual multiply accumulation step, we tried to kind of build the architecture around how you would like do it by hand. So you would have like a column vector multiplied by a matrix, and you kind of do like each column and row multiplied at once. So we have like 4 multiplier units that are taking in 1 vector at a time, and they each multiply it with 1 row of the matrix, and then add them together to get the kind of final result for 1 vector. And then there's a second step on the right side of that diagram where it actually does the accumulation. And so our goal was to do like 1 vector complete computation for each clock cycle. And then you'll see kind of in our results how that worked out.
It's a nice diagram. What software was this for the diagram?
Draw.io.
Yeah, just Draw.io.
And then I guess the what the Mac is doing, because we kind of have one state where it's loading in the initial matrix rows, and then a state that is actually multiplying the vectors through, and then a done signal when it's finished.
Okay, and then some bugs that I encountered when trying to get to work on the board was the memory synthesis issue where it mapped it to lookup tables at first instead of the VRAM block. I also created some latches on accident in the state machine that took me a while to track down. And then for some reason, when I simulated the full design, it was like one cycle ahead of where the final result was. So like I recreated the bug on accident when I was like messing with how many cycles the state machine ran for, and realized that the results I was getting back from the serial port were like doing 9,999 vectors, not 10,000. So then I just extended a couple cycles and it worked. And I guess it's not listed on here, but also our final design failed timing, but still worked. So I don't know if that's a bug or not.
Yeah, we can talk about that at some other time. I know you have some experience with this, Ben, but what was your process for discovering that you had, I think most latches are unintentional with FPGA design. What was your process for discovering that? Any tips you can share for others? If they have latches, their designs generally are not going to work.
Right. So I was looking through the synthesis, I think, and it had a bunch of critical warnings for like this register is clocked by like a non-clock signal. And I realized that what I had done was in my like if else statement, I had like if reset equals 1, like reset. And then, but for the else, I just had an unconditional else instead of else if, like when rising clock is 1. So it simulated correctly because it was a clocked process, but because I didn't have that else if like rising edge of clock or whatever, it just clocked it with a random signal instead of the clock. So I discovered it in the synthesis from the warnings that it raised, and then found that signal and realized I had messed up.
So the software time was about 500,000 nanoseconds, and then the hardware time was 10,000 or 100,000, and that meant that it sped up by about 5 times, which matches our expectations of a 1 vector product per cycle.
This is our demo.
If it works. Okay, cool.
Always test your YouTube or videos beforehand, because I may need permissions to access them and things like that. This one looks like it works. Yeah. Shaky hands.
Sorry. Maybe I'll use a GoPro.
Yeah, well, use like a little stabilizer mode on your phone if you have. Cool. That's always very satisfying to see, isn't it? And I know demos for future ones will be much different from every other demo. It's going to look very similar to that, I know as well. Any questions for group 1? Okay, so in class, as we're limited on time, we can't do a full round of applause, so we'll just do a single applause. So, good job, team. Wait. That was really bad from a timing perspective. Let's try it again. Good job, team. All right, great. Team number 2, come on up. Should just be the very next slide. You can advance one slide. You have to move the mouse out. Okay, great. Feel free to get started.
Okay, so I'm Jan. I did top-level design.
I'm Joel. I did some of the finance step machine design and the hardware integration.
And I'm Long. I helped Joel with the FSM design and some debugging.
So we started doing the finance step machine crowd working. We decided to pipeline it to get the 1 vector each clock cycle. At that point, it's like we're reading from the memory non-stop. So it's like, how can we speed that up? You know, there's different ways to do that. Easy way is to have more read ports. So using get more read ports is just to duplicate the memory. So we ended up having 10 DMEM LEDs in the design, each going in its own pipeline. So we had 10 pipelines going at the same time. Then at the end, it would add those 10 pipelines together. And we had to do that addition in 2 steps. And that was just because timing failed to add those 10 pipelines in 1 clock cycle. So adds half, and then on the next clock cycle adds those half to the rest of the pipelines.
We talked about this I briefly mentioned we did that CUDA code that was doing a vector sum, and I called it like a reduction circuit. That's another example of that. You have 10 values, you have to kind of reduce them all. Having like a tree of adders is a very common approach. But I have to ask, why just stop at 10 and not 11?
So at 10, it's thinking its next round number goes even into 10,000, and
okay, that's a valid reason.
yeah, it's also close to reaching the memory capacity of the FPGA. It has a little bit more space, but
Oh,
not too
because
much.
you copied all 10,000 vectors on all 10. You could have cut it in 10
Yeah,
pieces, well.
yeah.
Okay, great.
Did it take a long time to like synthesize?
Took like 20 minutes. So. Not too bad.
That's not a long time, by the way.
Yeah.
So yeah, it's a moderate amount of time, yeah.
So for some of our bugs, we had our done signal off by 1 cycle where it was triggering the cycle before it should have. So it was doing 10,000 vector, but then the done signal wasn't, it was triggered at the wrong state in the finite state machine. And then we also had a problem with triggering some of the correct control signal because we placed some of our control signal in the wrong state within the FSF. So there's some simple problems.
So yeah, the single pipeline, then about 100,000 nanoseconds, and then 10 pipelines was 10,000 nanoseconds, which gave us that about 10 times speed up that we expected.
Any questions for this group? So one thing you'll find with block RAM is there's a certain physical unit or series of units on the FPGA. The synthesis tools, assuming we code it correctly, are pretty good at figuring out how many of them you need, how many of those little units that you need to get what your design requires. And so the idea of replicating 10 DMEM modules works, so it's great. You could also just say, I want a single DMEM module with a really big data port or some other modification of the input signals to that. And then the tools would take that and kind of divide it for you and give you as many of those underlying block RAMs as you need. But this works pretty well. So 10x speedup is pretty impressive. All right. No questions for the team? All right. So far, it's the fastest one so far. So way to go. Okay, we'll work on that. All right. Team number 3, come on up.
I'm Aiden. I did a lot of the RTL and finite state machine design.
I'm Sid. I contributed electrical lab for it.
I'm Shreyas. I did most of the debugging. So
So you're the test engineer, he's the
Yeah.
design engineer, you're the project manager for the team. So that works.
Okay, so this is a diagram of how it works. The squares are pipelines portion because we initially designed a finite state machine, but then it was really easy to translate it over to a pipeline after we got through the first 3 stages. So in the first 3 stages, we just read in our A matrix, and then for a pipeline, we had our first step, which was read the X matrix. The next step was we multiply the X vector. We multiply the X vector by the A matrix, and then we added the multiplied matrix in steps, just because that was easy to do when I can't figure out how to add 4 vectors in one operation.
So the point I want to make, and I think your team, figured that out as you were designing this. I think oftentimes in like introductory digital logic or design courses, you're taught, oh, you have a state machine design, or you have a data flow or pipeline design, and the impression you're left with is it's sort of one or the other. Like you've chosen one or you've chosen the other, or you've chosen behavioral VHDL versus data flow or some other structural VHDL. It doesn't ever have to be one or the other. So it is very common, and if I were to look at your code, probably what you wound up doing here, that to have both inside either a single module or inside a single design, where you have your data flow VHDL describing some pipeline or some other just logic, the math that your design has to do, and then you have some behavioral VHDL describing a state machine that's controlling that logic. And so it can kind of be left sort of as orthogonal concerns. How do I get data coming in and data coming out? How do I control that via muxes and write-enabled signals and things like that? So you can always do both. You don't have to decide on one or the other. Just draw it out and then determine what your design needs to be, and you should be able to find VHDL that gives you what you need for it.
So, one challenge, I just implemented it wrong at first. That took a lot of time to fix. I just didn't accumulate it. That was annoying.
Then you could have just done the last vector. That would have been very fast approach.
Shreyas,
Yeah, so I was debugging the count signal done. So we weren't taking it into account that when we put out the result, the done signal had to be set to 1. So we were setting it at the wrong time, and count done signal we declared it as just 11 bits, and we weren't able to get it to run for 10,000. So we had to modify the declaration, and then we had going.
I put some other things on there. So testing, I wrote a TCL script. It was really nice. And then pipelining it was pretty easy, just from the finite state machine that we had.
Have you done this before, writing tickle scripts for automating stuff, or what course, or what experience?
No, I just did the forcing and then I copied the TCL test generation.
Well, that's what I want people. That was the point I wanted to make. So, Vivado, for all of its faults, like most CAD tools, though, is everything you can do in the GUI. Like any button you click to do anything, emits the equivalent tickle script for what it would mean to automate that via just running a script. And yeah, as you're first debugging a design or testing a design, it probably makes sense to still kind of do it manually and set your waveforms and set your inputs and test it that way. But once you know that you're in this loop of like test, modify, fix, retest, you're gonna want to take all those commands you use and just put them in a file. That's all you have to do, right? Copy, paste those commands, put them in a file. That's both for simulation as well as for like post synthesis testing and post design testing, and that'll save you a ton of just user errors and just make it much quicker to go from, okay, I have an idea for how I want to fix things, I want to change count done or something in my design. That once you have a nice script, that takes you like a minute to test out that idea versus someone else who's just remembering where to click, because it is a lot of clicks if you want it set up exactly the way you want. You want to load the simulation, you want to simulate for 100,000 cycles or whatever, 10,000 cycles or whatever it winds up being. You want to view and zoom in and color code the results this way. That can all be totally automated so that when you have an idea, 30 seconds later you know whether it worked or not. Another group who doesn't try that kind of automation is taking them 10, 15 minutes. That kind of adds up over the course of a more complex lab than this one. So you maybe don't automate before you understand your design a little bit, but once you know what you're looking for, start writing tickle scripts, copy paste the result of what you're doing manually, and you'll save a ton of time by the end of the semester doing that. So I'm glad you discovered that already. It'll become pretty important as we get more complicated looking data.
Then for results, we got about 0.1 milliseconds. I think that's the exact same time as group 1. We had some slack, which was cool. Could get down to 7 nanoseconds. So yeah.
Other questions for this group? No, don't get ready to clap yet. I have questions. It's warming up. So Slack is a funny thing. Okay. not entirely a digital design course. So when the tools report slack, that is their estimate of, for your 10 nanosecond clock or 100 megahertz clock, here's how, by what margin it was able to make that for all the different paths in the design. So interesting enough, your team reported negative slack, group one had bad slack, or didn't meet timing, but yet both designs were basically the same, right? And I would think within one cycle or two cycles, every design based on that state machine should be basically the same here. But there's a couple things. So first off, when the tools are reporting that slack, they do it at two different places. They do it at the synthesis time when it's just trying to analyze your design, and then finally when it's trying to map it physically to where on the FPGA the individual logic blocks are going, it gives you a much more accurate estimate at that point. But in both places, it's just an estimate. It's just estimating whether or not the design will meet timing in reality or not. And oftentimes, I think by nature of the tools, it's a very conservative estimate. So it is oftentimes the case that the tools will report that it missed timing and still sort of work. The timing is also a function of operating conditions. So it could be group one's design will work for 3 hours, and then the chip heats up a certain amount, and then it'll stop working, or it'll move into a different operating environment, or it'll switch from one board that has a high-end engineer or high-end FPGA to one that was actually an engineering sample that Xilinx just tried to pass to us, and it won't work on that second board. So there's a little bit of risk in not meeting timing. And the other risk, I think, is the tools just wind up churning a lot more in really trying to meet timing if they can't. So your runs will just take that much longer if the design is not meeting timing. So for most of the semester, you should aim to try to meet timing. You should be able to meet timing in your designs. What you could have also done, you don't have to, what you could have also done for this one is then recognizing, well, what was it, 30% met it by 30% timing or something like that. You could have then tried rerun synthesis with 125 megahertz clock, and you should have gotten, that baked-in speed up kind of for free from the same exact design at that point. Otherwise, this is a good, nice, competent job, and way to go, team. Good job. All right, last but certainly not least, group number 4.
Okay,
There we go.
we're group
Great
4.
energy, thank you.
Yeah, let's get it. It's Tuesday. I'm Will.
I'm Brandon.
I'm James.
We didn't really have individual roles. We all just kind of crowded around the computer and, worked
And by
on
the
it.
way, I understand that as well. So if your team's struggling with that part of the presentation, what role do I assign myself? You're all just collaborating engineers. Assuming that's true, you're all just collaborating engineers. That's
Yeah. That made most sense for us at the time. We all kind of found a nice corner in the lab, and it was fun. So we did a fun little FSM. Everyone else did like fancy pipelining and complicated stuff. We went for get it done first approach, and that took us the whole time. So we ended up with a 7-state FSM. Tried to get some of those inner loops unrolled so that we could, attempt to optimize it a little bit. We are loading multiple of those vectors at a time. We used both outports. I didn't even think you could copy the DMEM. That was kind of clever, you guys. Group 1, or Group 2, sorry, getting those 10x. But, yeah, here's our fun. One of you two want to go through the diagram here?
Yeah, we have 7 states, and we probably could have condensed or rearranged some of it for a better speed up.
Oh. They're 8, not 7.
Well, we index by 0, I guess.
There you go.
We spent a clock cycle in state 1 waiting for the memory fetch. We had a dedicated wait for the memory, the clock, which could have been avoided, maybe not.
We were having a lot of,
debugging issues.
yeah, we were having trouble with that, where it
Yeah.
wasn't moving to the next memory index, the address. So
But we did unroll some things, so we kind of read the entire X vector through our memory, and then we multiplied it all at once, and then accumulated it all at once in state 5 and 6. And 6 was kind of like our point where we like branched off into the other states.
Cool. So, one of the, probably what we sat most of the time in our second Wednesday was just like incrementing the done timer up and down, trying to get everything our actual final output started out being like off by 2. So the last 2, memory that we read from for X, I believe, was like just 0, 0, 0. And so we were like, oh, what are we doing wrong? We counted it back to, and then we didn't go far enough, and whatever. You get the
If you
idea.
had too many zeros, that shouldn't have impacted the output, right? So that would have been.
Could have been
If
fine.
you're going too many cycles, it would have been okay for this one, but too few cycles, like.
Yeah.
That would be the issue.
We had an off by 1 bug, and we were trying to fix that, but we had other bugs that were also impacting the output. So we thought it was just an off by 1, but it turned out to be like a couple other things too.
Yeah, everything was wrong instead of just one
that was
thing.
kind of a pain. And like we had a lot of just tedious trial and error testing, debugging, like, hey, does this work? Let's test it. Hey, does this work? And there's a lot of back and forth that was kind of time consuming.
Yeah, honestly, in the end, our crowding around the computer, the collaborative approach didn't really give us enough time to do anything other than sit together.
I think
and
doing that
complain.
helped a lot with squashing a lot of the bugs before they became problems. But that you just lose like the simultaneous workflow of like breaking things up. So I think that's what we're going to try to work on for this next lab.
And as your synthesis times get up into that 20, 30-minute range and beyond, you definitely want to have a plan for that. Okay, somebody's going to hit go, but sitting here and staring at that isn't going to get anything done, right? So what can we do, either next iteration of design or documentation, or work on some other aspect of the project so that you feel like your time's being, productively spent, and it's not just a finite state machine that, it just takes too long otherwise.
Yeah, so we did way slower than the rest of you folks. So a whopping 1 millisecond runtime ended up being longer than the software. So that's not good. But all the values are correct, and it's running, that's for sure. Yeah, so we didn't optimize very well. I don't totally know why it didn't work faster, but it's probably to do with how we organize
So,
things.
okay, I'll pose that question to the class. And you guys are done. Let's get done first. Let's get them. Wait,
I think you have one more slide.
Oh wait, sorry.
Take it back. Do we have one more? Oh yeah.
These were like things we want to improve in the future. It's just like we said, write more things out, like our pseudocoding calculations, and then breaking things down into like different
Coding
sections.
calculations, pencil and paper can be critical for MP-1.
Oh yeah. We screwed up the matrix until Brandon went like home one day and just all better. Yeah. James did too. You both like actually wrote it down on paper. That's my fault. I didn't do any paperwork.
So when you say pseudocode, so going from drawing out the finite state machine and everything, and then going to pseudocode, and then going to VHDL, what does pseudocode look like? I've never thought of that.
I was thinking like we have like our diagram, and we have like our outflows.
Right.
Pseudocode I kind of meant more in line with like our calculation of like, okay, we take this value, accumulate it with this, and then we transition. Like the if-else blocks that we have within like the process, within each state. What does that look like? Not necessarily how we get from one state to the other, just like within that state, what does that code look like?
Okay, so just like the logic in that.
Yeah, the logic in each state.
Makes sense.
Awesome. Thank you, team.
We got 2 of them.
Let's do a little bit of a postmortem of all of these. I like the pseudocode idea. I think if you look back to, thanks team, if you look back to where we were with the in-class exercise where we were doing it on pencil and paper, that was very much a pseudocode approach. So I would say, if you have a really, really detailed state machine, then there is no pseudocode needed because the state machine is effectively the implementation. But oftentimes, just as we were getting things done, there's kind of an intermediate stage where like the state machine's kind of dodgy, and then you still have to kind of work out like, okay, what does it actually mean? When will I go from state 17 to state 18 here? What math should be happening to allow that to happen? And then the pseudocode approach, as well as the paper and pencil calculations, are going to be pretty critical here. Why do we think the result? Not that the result is bad. The result's perfectly fine. Why do we think it's not able to beat software? We always think hardware is faster than software. What happened for this particular design? Nothing wrong, by the way. There's no flaw in the design. But why was the result slower than the software equivalent? Sure.
I think when I was looking at their diagram, like the loading from memory, it seemed like they might have an extra cycle to wait for memory fetch. Maybe if it, like the cycles weren't matched up quite correctly, or there might have been like an extra register somewhere on accident.
I think that's not a bad way to think about it, like off like an extra cycle per iteration. Would add up to another like 10,000 cycles. So not I can't do the.
That wouldn't be the whole thing.
Yeah, I can't do the hex math in my head either in terms of what that number would be without that extra cycle. Probably pretty similar to. I forgot what the number you had here. Well, either the first or team 1 or team 3's initial number here. Another way to think about when you look at this diagram. Again, there's absolutely nothing wrong with this diagram. It's a perfectly fine diagram. This kind of approach, this kind of iterative approach of read value of A, read value of X, multiply A times X, accumulate value in Y, store value in Y. That is a very software kind of approach, right? That is just a sequential kind of software-like implementation for how to do this matrix vector accumulation operation. So it's hardware, but it's also can be very directly compared to like a software implementation as well. And that C code, that software that we have compiled, is also doing exactly that. It's not doing so via an explicit hardware state machine, but it's doing it via assembly instructions, which ultimately are implemented via some hardware-like concept, right? So it's load from memory via a load instruction. It's multiply using a multiply instruction. It's add using an add instruction, and store using a store instruction. So as we implement hardware that looks like this, or is just kind of a straightforward, straight line, sequential state machine implementation, we wind up implementing, very slow processors, basically, right? Because it's doing the same thing our regular CPU is doing. What is the other key difference between probably an Intel chip on Xilinx or Cougar 2050-07 computer versus this FPGA implementation? So one is running assembly code, the other is just directly encoding a state machine. But what's the other big difference between those two processors? There's another big difference. One's a lot more expensive. One you designed yourself, the other one you're just running code on. But there's another really big difference between the two that would lead to performance. Yours is application specific. That one is general purpose. So yeah, by all metrics, this is not as good as an Intel processor, but that wasn't our goal. Just in terms of the hardware characteristics of your Intel processor versus your design that you have here. Yes?
Is it because the Xilinx board is supposed to act more like a GPU than a CPU, since that does more parallelization?
That's a consideration that's going to be critical for us. It is a co-processor. Getting data on and off is going to be a real bottleneck for us. This one doesn't have a data bandwidth issue because it's all on chip. We put all the stuff on chip. We never go off chip. But even staying on chip, what is the big difference in terms of the fundamental design characteristic from, let's say, a technology node layout or performance perspective? Yeah, the clock speed is significantly slower, right? This is true in doing any kind of application acceleration, but specifically for this one, it's really kind of straightforward. I don't know the clock speed of the Intel chip on there, but 3 gigahertz is a good estimate. Maybe it's 2.6, maybe it's 3.4, but 3 gigahertz-ish for that. What is the clock speed for this design? Well, that one we know. It's 100 megahertz because we set it to be 100 megahertz. And for the one team, maybe you tweak it to 125, but you're not tweaking it to 3 gigahertz, right? You're going to tweak it a very modest amount here. So what are you really facing, even with this relatively, low overhead straight line implementation, is you're already facing kind of a factor of 30 that you have to overcome, right, in terms of performance versus software. If your software on the Intel processor was doing just exactly this, it should be roughly 30 times faster. There are other considerations. The vectors being loaded in software, have to go through cache, and they may be missing in the cache, and it could take 100 cycles to access that data. So there's factors that lead this to be not, 100 times slower, or what did I say there? 30 times slower, but at least it could be maybe 10 times slower. But you're already kind of facing that from 3 gigahertz to 100 megahertz. If you want to beat software in terms of a conventional processor implementation, which is not generally our goal this semester, our workstation is going to be faster than the FPGA board we have next to it. One costs several $1,000s, one costs $120. So we're not going to beat it. And even if we had a really high-end FPGA, the amount of design time we have isn't going to allow us to beat it, and the resources we have aren't going to allow us to beat it. But we always are kind of facing that direct comparison of 3 gigahertz machine versus 100 megahertz machine. You may learn when you take an architecture class that, clock frequency is not performance. And that's one of those fallacies you learn in the Patterson and Hennessy textbook. That is true. I'm not saying that's not the case. But at the same time, you still have one design that's clicking along this fast and another design that's clicking along at this much, 1/30th of the rate. And that does have implications for resulting performance when your implementation otherwise looks very similar to what an assembly straight line sequential implementation would potentially look like.
So what you're saying is don't code it like it's software. We need to design hardware.
Well, now I'm going to speak out of both sides of my mouth, right? Because for this class, our primary goal is correctness, getting it to work, right? So this is always valid. That's why I kept trying to say, Group 4, you did perfectly fine, you did great. Our goal is always to get it working. I think that will be your primary, struggle this semester, is to get the stuff working. When we then have time, we really want to consider performance. We get the baseline version working, it's potentially quite slow. Now can we kind of crank it up and look at what kind of assumptions can we now break compared to what the software implementation would be doing. And here I'm very happy to go back to Group 2's design here, which this is very nice to see, that you just recognize that there's, and we talked about it in class as well, there's a lot of parallelism in the design that we can start to take advantage of. There is 10,000 elements of parallelism in the design, right? So in theory, although it would require a little bit more, experience with doing FPGA design than I think a lot of you probably already have, but in theory, that's kind of our upper limit of what we could do here, that we could do all 10,000 vectors in effectively just a few cycles. And if you look at prior somewhat insane TAs who were involved in this course, that's effectively what their design was doing, and the result was just a few handful of cycles to get the entire design implemented. You did not have to do that, so it's okay, but this is something along these lines, maybe even cranked up to 11, which is always fun to see, is where having a custom hardware accelerator design makes sense versus just running things in software. Because even though we're facing this 30x trade-off of clock frequency, if you can get more than 30x of parallelism, it may still then be very much worthwhile to use a custom accelerator versus a just software implementation. And this goes to our kind of motivation for GPUs as well. Let's talk a little bit more about just kind of the background technology. Again, one just final syllabus reminder is MP-1 starts tomorrow in lab, but I would make a mental note that MP-1 starts right now for you. By the way, that's also a way that team you can help contribute to your team as MP-I is finishing up and the team is just kind of finishing up last touches. Maybe one person can look ahead to MP-I+1 and start to do the pre-lab. It'll be one submission of the pre-lab per team. So technically only one person on your team has to do the pre-lab for MP-1. But I think it will be to your team's entire benefit for everyone to at least read through the lab, skim, read, and discuss as a team. That'll be a good use of your time. You'll just be more effective in the lab tomorrow. The only challenging part is, depending on how late of a night you were spending on Monday night, you may not feel super enthused to be working on this class again on the Tuesday afterwards. But just do your best to kind of manage your time collectively as a team. That maybe it's a late night, but one person then looks at the lab for the following Wednesday. Jeremy, the TA, will be looking at your pre-labs tomorrow, first thing in the lab section here. We won't go too much today about this, but I just want to make sure we kind of get a little bit back on pace. You know, a big chunk of MP-0 had to do with interfacing with memory. Now, the block RAM technology we were using kind of makes that relatively straightforward, right? The interface to that block RAM, which is implemented using SRAM technology, is you provide an address, you provide an enable signal, and maybe a write enable signal, and you get your data out of cycle later. That's a very nice, straightforward interface. And you may say, why don't we just do everything with SRAM so that can be our interface to all memory? In practice, there's a density issue here. We won't go into the low-level layout of SRAM cells. You may have seen it in other courses. It takes a lot of transistors to get 1 bit of storage in an SRAM cell. Much more commonly, for the memory needs we have in computer graphics, where we talk about the size of what one individual frame buffer may need to be, and we recognize that there's going to be potentially at least 2, maybe 3. And that's just for displaying the final image. All the other memory that our GPU is going to need. Much more commonly, we're going to be using DRAM technology instead. This is not a VLSI course. I think it's sufficient from our knowledge basis perspective to recognize that we have 2 different types, commonly used types of memory in our computing systems. There are way more than 2 types of memory, but the 2 most common are still by far SRAM and DRAM. S stands for static and D stands for dynamic, but that distinction is not as interesting to us or relevant to us. What's relevant to us is twofold. One is the technology underpinning DRAM allows us to have a lot more potential storage of 1s and 0s for a relatively competitive amount of cost. The downside of DRAM is the underlying implementation, just from a VLSI perspective, as well as from a sort of a control perspective of reading and writing to it, tends to be a lot more complicated than your corresponding SRAM. Any SRAM you need in your design, which used for cache, used for some local storage, tends to look a lot like the block RAM style interface you used for MP-0. The trade-off there is the type of memory storage you're talking about for your SRAM is measured in kilobytes, maybe low order megabytes, but that's about it in your design. That's not going to suffice by and large for our frame buffer purposes. We did this napkin math a couple times already in terms of for a 1920 by 1080 or 1224 by 1024, 1280 by 1024 frame buffer, knowing that we need a lot of those frame buffers, we're going to need more than that amount of memory. And in designing any embedded system, that's kind of one of the first considerations, and a GPU is no different. What memory do I need in the system? How am I going to manage all that memory? How am I going to interface with all that memory? So suffice to say, I think for our purposes, for anything graphics related, we have to go to DRAM pretty quickly. That is going to be a fundamental complexity in all of your designs going forward that MP-0 didn't have, where all of our memory was kind of resident on chip, stored in SRAM. You provide an address, you get a data back out. For DRAM, it tends to be quite a bit more complicated than that. It's still address and enable signals, so that interface aspect of it doesn't necessarily change. But there's multiple steps involved. I don't think we have to go into all the detail here. But just like there's companies that are dedicated to actually designing DRAM. So Micron's a decent example. Flash memory DRAM. Anyone here worked for Micron or interned for Micron? It's supposed to be a really great place to work. They focus on memory technology. That's why they exist as a company. There's sufficient complexity in interfacing with DRAM that the intellectual property to do that is itself its own separate segment of industry, of companies who focus on, at least in part, designing the IP cores to be able to interface efficiently and effectively with DRAM. We are using Xilinx's solution for interfacing with DRAM, which tends to hide some of the aspects of row access lines and column access lines, and you have to wait 3 cycles to pre-charge, and then you can provide the address for the row, and then you provide the address for the column. If you look at a Micron data sheet, you can review it if you'd like. There's several hundred pages long, because the timing and the electrical characteristics tend to be really, really technically detailed. This would be a lot. Just building an FPGA designed to interface with DRAM would take us a large chunk of the semester. So we can't afford to do that. That would be the entirety of what we're doing this semester. Could be a project for some other digital VLSI type of course. I think it's sufficient to say, I don't think we need to go through all the details of it, that one could build a state machine to kind of control that kind of interface to DRAM. There's companies that exist to provide effectively those state machines for you. I think more importantly, just understanding that once you have DRAM, you get the capacity that you need. You also potentially get some throughput that you need, but the trade-off is that complexity. Other trade-off, which isn't as obvious because there's some gaps intentionally hidden here in this state machine here. The other trade-off with using DRAM is you don't get that like kind of instantaneous result back out. Most SRAM you use in your design, you provide an address, you get the data back next cycle, 2 cycles, 3 cycles, handful of cycles later. The whole reason in our computing systems we have these SRAM caches is because when we have our backing data stored in DRAM here, now you're talking, depending on if it's sort of a randomly accessed value or if it's a consecutive value, sequential value, you're looking at potentially 100 cycles, 200 cycles of latency. And that's going to fundamentally influence a lot of what we're doing in our design as well. A big part of embedded system design, of GPU design, is to keep as much data flowing nicely through the pipeline as possible so that we don't have to go off to DRAM all too often. Every time we do, we're going to have to pay a penalty, both in terms of the complexity of interfacing with DRAM, as well as potentially the latency of interfacing with DRAM as well. I think it's sufficient to say that it's a different type of memory technology than your MP-0 memory you use. There are many, many different variants or flavors of DRAM. This is not a VLSI course. Being aware of the broad numbers in terms of what is possible from a bandwidth perspective can be useful for just trying to do a high-level estimate of performance. So DDR DRAM, so that's DRAM that's at a dual data rate. This timing diagram may show this. It kind of does. This is a differential pair of clock signals. So in reality, there's not just one clock. There's a pair of clock signals, and they're always purposely out of phase with each other. That allows you to effectively double time the logic so that you have a 100 megahertz clock, but you're accessing it as if it were a 200 megahertz clock. Anything that is DDR DRAM is using that dual data rate. There's standards that emerge via consortium to determine the next generation. There's standards that are associated with just general DRAM. There's also graphics DRAM. So if you see the term GDDR, that's referring to DRAM specified specifically for graphic signals. And you can get a rough order estimate of the type of bandwidth that is possible here. I gotta be a little bit careful with my bits versus bytes, but you can kind of measure it there based on the number of data lanes that are available, then the clock speed that those data lanes are operating at. Of all these different versions, it really depends on the device that you are interfacing with. The one that probably matters the most for us this semester is DDR2 800, which is nowhere near state of the art, but for the cost of the board, it's sufficient. That is what we have, right, on the Nexus video FPGA board that you're implementing these designs are. That maximum transfer rate is one of the fundamental limitations of any design we're doing this semester. How fast can we get data in and out of our frame buffer? The story's a little bit uglier than that as well, because when a spec sheet like this mentions a maximum transfer rate, in theory, there's no difference between theory and practice, right? But in practice, there is. So that's your best case scenario. Everything is perfectly aligned and sequential, and everything gets out as quickly as possible. In practice, maybe you cut that number in half, and that's the kind of throughput you can get for transferring data on and off our memory. So in terms of the performance of our resulting designs, where you have your theoretical max of 6.4, you have maybe half of that in practice. If we go back to what we potentially need for our particular frame buffer, we are already using a pretty big chunk of this just to read and write from our frame buffer without doing any actual graphics processing whatsoever. So this is kind of a limiting factor of the technology we have in this class, that we have to interface with DRAM because we need to be able to store a large amount of memory to get work done. There's then the complexity of accessing DRAM. There's an IP core we use to interface with off-chip memory. It'll provide an interface that's a little bit easier than this style of interface, but it's still more complicated than your SRAM interface for MP-0. And then the other limiting factor is, we are going to be memory bound for a good chunk of the type of applications we're interested in doing. Just being aware of that, I think, is probably sufficient for now. Our frame buffers are going to be in DRAM. All of our cores that want to interface with graphics-related data are going to have to go off into DRAM and grab that data. We're pretty bandwidth limited as we design our pipeline, right? We have the logical graphical pipeline, and then we have the individual components that themselves may be pipelines. We may want to implement a cache, but beyond that, we may want to keep data just inside that pipeline as long as possible before having to either read or write from our off-chip memory due to the complexity and the performance considerations of doing that in our design. I have a demo showing kind of bandwidth testing on a modern GPU system. I think I'll skip it for now. I can bring it back on Thursday as we continue on this particular topic. It just is, it's a truth in designing systems and measuring systems. It's actually not that straightforward to even know exactly how much bandwidth you have. It's not that straightforward to saturate a bandwidth link and to write an application that does so. So this example that I have from the CUDA SDK is showing an attempt to saturate the throughput between your device, your GPU's memory, and your host CPU's memory here, and to show for that particular GPU what kind of throughput is possible here. Maximizing your throughput is a fundamental challenge in designing any computing system. Your GPUs are no different. I'm also going to quickly skip over display technologies. This could also be its own course where we could talk about cathode ray tubes and liquid crystal displays and plasma displays and LED-based displays. I'll talk briefly about CRT-based displays because what seems to be an antiquated concept is actually quite relevant still. So at a very high level, you have your RGB signals that are coming in off your interface to the actual display. The so-called electron guns, which are going to heat up anodes, and they're going to shoot towards this actual screen that has some phosphorance characteristics to it, and it's going to have these kind of directions of those electrons that are getting sent out, and it's going to be doing that raster scan pattern. From the upper left, it's going to go row by row by row by row. That kind of fundamental concept of timing and interfacing is still in use today, even though we very rarely actually use CRT displays here. As we've gone to LCDs and plasmas and LEDs and things like that, you'd know if you have a CRT TV. Anyone still have one at home, a CRT display? Yeah, we're getting past the age where anyone still has them. They were very nice for their era. You would know you have a CRT if it was exceptionally heavy and large. That's how you know you had all that technology there. They also had very high capacitors to be able to supply the voltage necessary for the operation of it. So they're also very dangerous to take apart. So if you do have one, don't take it apart unless you know what you're doing. Even as we've gone to much more modern types of display, and the display technologies are continuing to evolve, and resolutions have continued to increase, that method of accessing both our memory as well as interfacing to the display really hasn't changed all that much. There are different ways of interfacing with displays, but by and large, if you take your laptop or take your computer and you connect it to a display via DVI and HDMI, display link cable, the physical signaling is quite different underneath the hood there. But the actual timing characteristics of that data that's getting transferred is exactly the same, or it's an evolution of the same way of interfacing with a computer as with the old VGA screen. So this term VGA graphics is still a relevant thing, even if the term VGA resolution is not one we typically use in modern systems. It is still a standard that models the timing inherent in like the physical retrace of a CRT, where there was something very physical that was going from left to right and from row to row to row to row. Even in a modern display, we can actually access all the pixels potentially in parallel here, and there isn't like a physical enabling of the individual pixels to turn them on and to turn them off. Even if we're not doing that anymore, the timing associated with sending that data still follows that methodology, or models that timing that's inherent in that physical process that was possible here. This is also something that just being aware of is probably sufficient for our purposes. It's the same kind of issue. We have this physical interface. We have an HDMI port on that FPGA board. We have to connect it to a monitor and hope that it works. The HDMI driver is really just taking care of that physical interface, making sure the signaling is at the correct characteristics. We still need to have some piece of logic on that board that is determining the right timing, that is reading data from memory at a sufficient rate to be able to keep the display fed, and it's modeling things like the period of time before we have an active pixel, our front port here, the active video frame where we're actually displaying stuff on the screen, the time required to kind of go back to the beginning of the next line as we go line by line by line, and then at the very end of the frame, the time it takes to go back to the very beginning of that next frame. Again, even in our displays in 2050 Cougar, we don't physically need that much time to go from the upper left corner to the lower right corner. The standard we use to interface with those monitors still takes that kind of timing into account. So there's a horizontal time and a horizontal retrace. There's a vertical timing and a vertical retrace. That's the so-called VGA standard for interfacing with computer graphics. We have a board that has an HDMI port. There's a chip on the board that deals with the actual physical signaling of HDMI. On our FPGA for our graphics designs, we still need a hardware module that can interface to our DRAM, that can read from the DRAM, and can generate effectively this signal for the resolution that we are interested in. The reason I say that awareness of this is probably sufficient is because unlike potentially in other courses where we actually design that IP core, I've just provided that for you. That would also take a couple weeks for us to design that as a class. So it's there, we have to be aware of it. We don't have to design it ourselves, so you don't have to be as fluent in VGA timing as you would potentially need to be if you were taking, for example, CPRE 488. But then to control display at different resolutions, the primary difference is you need a different size frame buffer, so you need more memory that you're going to be reading from, and then the timings just tend to be different for different standard or quasi-standard type of resolutions. This timing calculator, the link is in the slide, you can grab it from Canvas, is really good for kind of just calculating the actual signals. It's just a big spreadsheet for the actual signals you need to generate, and also gives you a really nice estimate of what kind of clock rate something is going to have to correspond to, and how much bandwidth you need to be actually to read from a frame buffer at that appropriate rate. Because otherwise, that's the only difference. Between 640 by 480, old school VGA resolution, and what we call high definition 1920 by 1080 resolution, the primary difference is the size of memory we have to read from, and also the timings associated with how big our front porch is, how big our back porch is, the time it takes to scan this region and scan this region, and the time it takes to go back to this particular region here. It also tends to specify a so-called pixel clock associated with that, which is to be able to get data onto the screen within the amount of time needed for a single frame. Here's roughly how quickly you need to generate one pixel to get that result back out. The signals also have some error tolerance. So even if for 640 by 480, there is technically like a 25.25, it should be listed here. That's actually this is the one we usually use, 25.175 megahertz clock. If you provide a 25 megahertz clock, it'll usually work well enough. So there's some tolerances built in here. This is the timing calculator, just a random one found online. It's actually kind of useful to get a good feel for the video system you want to design, what kind of bandwidth do you actually need, and then consequently, what are the signals needed for an IP core that was going to drive a monitor at that particular resolution. So for 640 by 480 resolution, you would take this set of signals here. Some of these are measured in megahertz. The rest are going to be measured in either pixels, or you can think of that as just clock cycles as well. for that particular resolution, here's how many cycles you need to do the various steps here. Let's just actually preload it and make sure it's correct. Yeah, that one's fine. As you start to go to higher resolutions, so 1080p at 60 frames per second, which is roughly what we are doing for this simple graphics processor here. What will change is the clock frequency needed to drive that circuitry. 148.5 sounds correct to me. And then the number of cycles needed to go from each line to line, and then the amount of time needed to go from the end of one line, end of one frame back to the beginning of the next frame here. And one would need to design an IP core that can basically take those spreadsheet values. It would just be a state machine like anything else. It would also need to interface with that off-chip memory, read in pixels, output those signals at the correct rate to be able to drive your resulting design. What I like about this spreadsheet is not only does it, this website, does it not only provide the spreadsheet for VGA timings, but you could just literally get a spreadsheet for that. It also kind of compares it to various kind of ways of interfacing with a monitor and whether those specs, in terms of the bandwidth of those interface specs, would be sufficient or not for this particular VGA resolution here. So all the various different display ports, HDMI cables, things like that. It also gives you an example, for example, if you wanted to interface with the monitor or with the system at that resolution and you wanted to use a 1 gigabit Ethernet cable for it. This claims no, that's not sufficient because the math is, if it's a 1 gigabit Ethernet, 900 and some change megabits per second of actual data, and again, that's in the ideal scenario of what you can get back out of it. And if we were to do the math of what this would actually require, that's 1920 by 1080 times 60, and that's going to be more than that 900 megabits per second you would need to transfer data on and off here. So that's kind of also the answer to the question of, we have this co-processor interface. In our circumstances for CPRE 480/580, we're using a gigabit Ethernet as our interface to the FPGA design. It's really not sufficient for us to drive the resulting display. So real-time graphics where we're sending all this frame data on a frame-by-frame basis is not going to be able to use the gigabit Ethernet connection. Or if it is, it's going to be quite laggy and slow, and you're going to notice it. One of the very first MP-1 applications to test that your board, actually has a valid bit file on it, is doing essentially that. Take this image, encode it as just the corresponding pixel values we want, send it over Ethernet to the resulting FPGA board, see that result displaying on the screen. This doesn't quite give an answer because this says, well, we wanted 60 frames per second, we're off by a factor of 3, maybe you can get 20 frames per second. Again, that's all ideal scenarios. There's a couple of factors of 2 built into that, so we wind up with about 1 frame per second in doing that kind of transfer of data. That'll be one of the built-in applications you'll have for MP1. Let's leave things here for today. Talk as a team briefly, have a game plan for MP1 pre-lab. You'll have a much more productive and, I think, enjoyable time in lab tomorrow if you've done that properly. Okay? Great job on MP0, everyone.